Well, now that we've mastered negative exponents and exponent rules, and we know how to add, subtract, multiply polynomials, we're going to talk about the last step, how to divide polynomials. So we're going to start with polynomials divided by monomials. This is going to involve some division. It's going to involve some negative exponents. And the next video we'll talk about long division of polynomials, which is quite advanced. We use it for a lot of things later on. So let's discuss dividing polynomials by monomials. Now, one thing that we know how to deal very well with dividing terms by terms, individual terms by individual terms, and separating factors and dealing with the numbers by division and dealing with the exponents through our exponent rule of subtraction. We're pretty good about that. What we don't know how to deal with is more than one term divided by one term. We don't know about that yet, and we're going to get there right now. It's not that hard, but the idea is let's break this down into something we're used to. Individual terms divided by individual terms. That's what we're going to go for. Now, how we get there, it really stems from this idea of having a common denominator. You see, the reason why these fractions are able to be added is because we have a common denominator. That's great. We know how to do it even. We know that if we have the same denominator, we can add the numerators and keep the denominator the same. That's fantastic. I'm not going to go any further. I don't care that this is really 4/7. I don't care about that. What I care about is if this is true, if 1/7 plus 3/7 is 1 plus 3 over 7, then the reverse is also true. Then 1 plus 3 over 7 can be split into two fractions, 1/7 plus 3/7. If we can put fractions together with a common denominator, then we can split fractions up through its common denominator and treat this as a common denominator situation. This idea is what I need you to get. If you get that, then you're done. That's exactly what dividing polynomials by monomials does. It separates a large fraction into however many terms there are in the numerator, that many fractions. A fraction for every term that's on your numerator. You know what's funny is, what I teach. I teach a lot of different levels. When we get to calculus 1 and 2 and 3, people often forget about this, that when you divide polynomials, several terms, by one term, it's this idea. You can always separate your fractions through addition subtraction and keep the same denominator for every one. It's just a common denominator. Why it works is because, well, if we have these two terms and we're trying to divide, we know that here we were able to take one fraction for every single term. 1 over 7 plus 3 over 7. We know this by a common denominator. But the same thing works here. We can actually separate this as x to the 5th over x squared plus x to the 3rd over x squared. It needs to make sense to you that, man, if I had a common denominator and can add those fractions together, then from the fractions added together, I can get two fractions with a common denominator. Now, why it's nice is because once you do that, we fall back into the stuff I've taught you. So once you're able to separate your large fraction into a fraction for every term that's on your numerator with the denominator as your denominator in every single one of those fractions, now we fall back a step and we go, well, can you simplify this fraction? If yes, then do it. If not, then you move on. Can you simplify this fraction? And then you try to simplify each fraction individually. What that does for you is that allows you to go back to your exponent rules. You're dividing numbers by numbers and using exponent rules, such as, hey, x to the 5th divided by x squared. We know how to simplify that. We know that we can subtract exponents, or think simplification. There's 5 x's here, there's 2 x's here. You're going to pair up 2 x's, there's going to be 3 left on the numerator. Either way, you're going to get x to the 3rd power. 5 minus 2 is 3, or there's 5 here, there's 2 here. Cross them out, you have 3 left on the numerator. Same thing here, x to the 3rd divided by x squared. Well, 3 minus 2 is 1. That's going to be x to the 1st. Or if you were to simplify it, there's 3 x's up top. There's 2 on the bottom. Cross out 2 pairs. There's only 1 left, x to the 1st on the numerator. That is how you divide polynomials by monomials, just term by term. That's frankly all there is. The things where people kind of mess up is they start trying to simplify here right away. Don't do that. You can't ever simplify across addition or subtraction like that. We must break up into a fraction for every term on the numerator and then simplify individually, every single fraction. The other thing is, please remember that, man, I'm begging that you guys remember the like term idea. Once we get down to addition subtraction, what we do with exponents is one level below. Unless your exponents are identical, you can't add or subtract. There's no way to change them with addition subtraction. So we're done. Those aren't like terms, you're done. If you want, why don't you try the next three? I'd pause it right now. See if you can do it. See if you can at least split up into however many terms you need, however many fractions for however many terms that you have. Here we have two terms. We have 4y to the cube, we have 8y squared over one monomial, a single term. Now, this kind of begs the question, can you do this if you have more than one term here? No. No, you can't. And that's why the next video is going to exist. It is for long division of polynomials. So when you have a polynomial divided by monomials, very specific, several terms divided by one term, we can use the idea of a common denominator to give us one fraction for every term we have. The denominator of every one of those fractions is going to be that denominator. That's how we keep that common denominator idea. The numerator of every fraction is going to be the terms. So 4y cubed over 8y squared, no problem. 8y squared over 8y squared, not a problem. We're making one fraction for every term that we have over the same denominator. Hey, you could add this together and get back to there, so why not be able to split it up? What that does, that lets you simplify every fraction that you're given. So let's start simplifying. Now, I'm not going to go back and reteach you how to simplify these terms. This is covered in some previous videos. What I need to remind you of is that we use exponent rules only with exponents. We simplify our coefficients normally. So 4 divided by 8 is 1/2. We can still do that. We can still simplify and get, well, hey, 4 goes into 4 one time. These are connected through multiplication. 4 goes into 4 one time and into 8 two times. We've done that many times. Simplify our y's. Hey, there's 3 of them here. There's 2 of them here. I would be able to simplify 2 pairs of y's, but there'd be y to the first power left on the numerator. So with our first fraction, the only thing left on our numerator is y. I had 2 here, I had 3 here. Even if you subtract, you can get that. 3 minus 2 is 1. So we have y to the first power. On the denominator is 2. That 1/2, that 2 is on the denominator. So we get y over 2 for our first fraction. The next fraction, man, you're dividing something by itself. You're going to get 1. So y over 2 plus 1, or 1/2 y plus 1. Separate into the number of fractions for every term that you have and simplify each one. 4 divided by 8 is 1/2. That's our 1/2 right here. 1y over 2, 1/2. We have y on the numerator, and then this gives us 1. Next up, hey, it works no matter how many terms you have, as long as you have one term on the denominator. We do. We have 5x. So we can separate into 1, 2, 3 fractions. We're going to do that. So we now have 3 fractions, 1 for every term, and just simplify the terms that you have. So I know that 5 divided by 5, well, that's 1. That's great. X squared over x. I have more x's on the numerator than on the denominator. How many more? Well, just 1 more. So I would be able to match up 1 pair of x's simplifying, but I'd have x left. So we'd really get 1x over 1. Now, we don't need all that. 1 times x is x. X divided by 1 is still x. So this whole term simplifies down to just x minus. Now, while 5/8 doesn't simplify, x over x does. We can simplify every single factor in a term if we've separated this. That was the whole premise of our previous videos, is that if we have factors, we can simplify the numbers and every pair of variables. So the idea is now, if we can make this 3 individual terms, then we can simplify each one by looking at the factors. So 8 over 5, no, that doesn't work. But x divided by x, yes, we can simplify that. X divided by x is 1, so we just have 8 over 5. Leave it. It is okay to get fractions. So we simplify 5 over 5, get 1. X squared over x, we now get x. That's great. So we're looking at every single term and simplifying that independently, just like we did in the previous videos. Now we have a minus sign, cool. 8 over 5, leave it. X over x simplifies, it's gone. Now the last one, we can always simplify our numbers, our coefficients, and our variables. So whenever we have things multiplied together, that's why we separated into terms, so we could simplify by that multiplication. This is 10 divided by 5. Don't even worry about the x right now. This is 10 divided by 5. 5 goes into 5 one time, into 10 two times. I can't simplify any x's. It's just going to remain on the bottom of the fraction. That would be 2 over x. That's perfectly appropriate. Now, it's not a polynomial by the nature of having a negative exponent. Do you guys see the negative exponent? This could be 2 to the negative 1. But this is the expression that we get from it. Okay, last one. You should have definitely tried this on your own. If you haven't, now would be the time. So we have 3 terms divided by 1 term. That's when this takes over. When we have a polynomial divided by a monomial, we know that by the nature of having a common denominator, if I have a common denominator, I can put fractions together, which means I can split them up by a common denominator. I can split up for every term that I have on the numerator. Your denominator never changes. It can't. Otherwise, you lose that common denominator and your fractions can't be split up. And now we simplify everything that we can. So basically what this does, it changes one problem into 1, 2, 3 simplification problems that you've already seen before. So simplifying our terms individually, we simplify our numbers. We always look at these terms as a grouping together of factors, as these factors multiply together. That lets us simplify our numbers. Exponent rules only apply to exponents. So 9 divided by 3, man, you're going to get 3. 3 goes into 3 one time and into 9 3 times. You're going to get 3 over 1, no problem. And now we have our variables. So we look at our coefficients and then our variables. T to the 4th over t squared. You could easily subtract. That's one method. I've shown that to you. So 4 minus 2 is 2. We're going to get t to the 2nd. You can also look at where more of your variable lies. So we have 4 t's here. We have 2 t's here. There's more t's on the numerator. That's where your result's going to land, is on the numerator. We can simplify 2 of them. There'd be 2 remaining. So our first term has a 3 over 1. Well, that's 3. And then a t to the 2nd power on the numerator. So 3t squared. Next term, well, let's look at that. If we simplify our coefficients, 6 divided by 3 is 2. We can divide that. 3 divided by 3 is 1. 6 divided by 3 is 2. So I know I'm going to get a 2. Now, t squared divided by t squared, no matter how you cut that one, that's great. Hey, 2 minus 2 is 0, t to the 0 is 1. Or if you just look at your dividing, hey, equal number of t's by equal number of t's, they're all going to match up. You're still going to get 1. Or divide something by itself, you're still going to get 1. 2 times 1 gives you that 2 right there. Lastly, I know we're going to have a minus sign. Simplify your numbers first. 3 divided by 3 is 1. I know we're going to get a 1 out of that. Now, how about that? T divided by t squared. You could get t to the negative 1. That's fine. Furthermore, by the nature of having a negative exponent, you would get 1 over t. I already know 3 over 3 is 1. That's fine. But we could get 1 over t. Or you think about it simplification-wise. Hey, there's 2 t's here, there's 1 t here. There's more t's in the denominator. The remaining t's are going to be on the denominator. We can pair up 1 pair of t's. There'd be 1 left on the denominator. Either way you go, you're going to get 1 over t. That's the resultant expression. That's all there is to it. So dividing polynomials by monomials, it looks confusing, but I promise you, when you get to calculus and you start doing integrals, Calc 1, and you get these things that look kind of funky and they're fractions, you go, what am I supposed to do with that? There's no rule for that. There doesn't need to be. Because if you can divide a polynomial by a single term and however many fractions there are for however many terms and simplify each one, well, as long as you know about natural logarithms, and you're going to get there, you can do some calculus on those fractions pretty quickly. And it all starts right here with dividing a number of terms by 1, creating several fractions, one for each term, and simplifying each one of them with some basic rules of exponents. Either simplification, wherever more variables are is where your answer lies, numerator or denominator, or subtracting exponents and moving negatives back down, and not applying exponent rules to coefficients. That is the idea.